why some theories treat black holes as cosmic memory. Imagine, for a moment, that you are holding a single page of a very old book. The paper is thin, slightly yellowed at the edges, and the ink has faded just enough that you have to tilt the page toward a lamp to make out some of the words. You strike a match. The flame catches the corner. Within seconds, the paper curls and blackens, the ink turns to soot, and what was once a page of carefully arranged letters has become a small heap of gray ash on the table. The room smells faintly of smoke. The words you held a moment ago seem, to every ordinary observer, to have vanished into nothingness. But here is something strange. According to the deepest laws of physics that we know, those words did not actually disappear. They are still out there. Not as words you can read, not as ink you can recover, but as information, scattered into the precise arrangement of every molecule of smoke, every flicker of warmth in the air, every photon that left the flame and went speeding off into the world. In principle, a sufficiently powerful being, with sufficiently precise measurements, could gather every smoke particle, every air current, every infrared photon that ever radiated from the burning paper, and reverse the entire process. The book would reassemble itself. The match would suck back its flame. The ash would recompose into yellowed paper, and the words would return, faintly, ready to be read again. This idea, that information is never truly destroyed, only scrambled, is one of the most cherished beliefs in modern physics. It runs deeper than energy conservation. It runs deeper than the second law of thermodynamics. Some physicists call it the -first law, because it feels more fundamental than the laws that already have numbers attached to them. Leonard Susskind, one of the great theorists of our time, treats it as something close to a sacred principle. Whatever else changes about the universe, the past is supposed to be preserved. The history of every particle, every interaction, every event is meant to be written somewhere in the fabric of reality itself. The cosmos, the bedrock principle suggests, is not allowed to forget. And then there are black holes. A black hole is the place in our universe where this comforting belief goes to die. Or, depending on which physicist you ask, the place where it triumphs in the most magnificent and counterintuitive way imaginable. For nearly 50 years, the greatest minds in physics have been at war with themselves over what black holes do to information. Stephen Hawking, in 1976, calmly announced that black holes are the universe's perfect shredders. They take in books, planets, dying stars, your grandmother's recipe collection, an entire civilization's worth of poetry, architecture, and song, and they simply erase the information forever. The past, in his view, could be destroyed. This claim broke physics. It violated the most fundamental rule of quantum mechanics, the rule called unitarity, which insists that the universe must always be able to remember what came before. And so began one of the strangest intellectual sagas in the history of science. A saga that has led some of the world's most brilliant theorists to a conclusion that sounds almost mystical. They now suspect that black holes are not destroyers of information at all, but rather the exact opposite. Black holes may be the universe's most efficient memory devices. They may be cosmic hard drives, holographic libraries, places where the entire history of everything that ever fell in is stored on their surfaces with a density that beggars the imagination. Every supermassive black hole at the heart of every galaxy may be a vast, silent archive, written in a language no one yet knows how to read. Whole stars, swallowed whole, their atomic composition and electromagnetic signatures and gravitational histories, all preserved in patterns of quantum information so dense that a single black hole, the size of our solar system, would carry more storage than every digital device ever built by every human civilization, combined and multiplied by a number that has no name. This is not science fiction. This is not the speculation of fringe thinkers or popularizers stretching for a dramatic angle. This is what serious theoretical physicists, working with serious mathematics, at institutions like the Institute for Advanced Study in Princeton, Stanford, Cambridge, Harvard, and Caltech, have concluded after decades of struggle. And the journey to that conclusion has taken physicists through some of the strangest territory ever explored. Through dueling postulates, fictitious firewalls, holographic projections, entangled wormholes, soft hair, fuzzballs, and tiny islands of impossibility hiding behind event horizons. It is a story of intellectual combat played out on chalkboards across 3 continents, with the very nature of space, time, and memory itself hanging in the balance. So how did we come to suspect that the darkest objects in the universe are, in some sense, the most luminous? How did black holes go from being the ultimate cosmic vacuum cleaners to being the librarians of reality? The answer involves a young graduate student at Princeton who was told he was almost certainly wrong. A thought experiment about flashlights that should not have worked. A famous bet that was conceded over a baseball encyclopedia. A 4-decade tug-of-war between 2 of the greatest pillars of physics. And a series of breakthroughs so recent that the ink on the published papers has barely dried. To understand it, we have to go back to the beginning, to the moment when someone first dared to ask a question so simple that nobody else had bothered to ask it. What happens to the information when something falls into a black hole? Where does it go? Could it, somehow, still be there, encoded in some subtle pattern that we have not yet learned to recognize? And if so, what does that tell us about the deep structure of reality? To appreciate why this question was so dangerous, and why it has consumed so much of the energy of theoretical physics for half a century, we have to first appreciate just how seriously physicists take the conservation of information. It is not a casual preference. It is not a stylistic choice or an aesthetic ideal. It is built into the bones of everything they believe about how reality works. In classical physics, the principle traces back to Joseph Liouville, a French mathematician working in the early 19th century. Liouville studied what happens to a cloud of points moving through the abstract phase space that describes a mechanical system. The multidimensional space, where each axis represents 1 degree of freedom, position, or momentum of every particle in the system. He proved something subtle but profound. The cloud can stretch, it can twist, it can fold itself into shapes of fantastic complexity, but the total volume of the cloud must remain exactly the same. No matter how scrambled things become, the underlying number of distinct states is preserved. The past is encoded in the present, even if you cannot easily read it. This means, in principle, that if you knew the exact positions and velocities of every atom in your room right now, with absolutely no uncertainty, you could calculate where every atom in your room was at any moment in the past. The information is all there. Time, in classical mechanics, is just a smooth, deterministic flow, and that flow is reversible in principle. The egg has not really forgotten that it was once unbroken. The smoke has not really forgotten that it was once a candle flame. The dust on your shelf has not really forgotten the journeys of the molecules that compose it. Every change is a transformation, not an erasure. Every event leaves traces that, given infinite computational resources and infinite precision, would let you wind the universe back to any earlier moment. When quantum mechanics arrived in the early 20th century, This principle was lifted into an even stronger form. The mathematical operations that describe time evolution in quantum mechanics are called unitary, and the property of unitarity has a beautiful consequence. If you know the complete quantum state of a system at one moment, the equations of physics let you, in principle, reconstruct the state at any earlier moment. Quantum mechanics, at its deepest level, is a deterministic theory played backwards. Every quantum interaction preserves something. Call it the information content of the system, or the von Neumann entropy of a pure state, which always remains zero, or simply the historical record. Whatever the language, the meaning is the same. The universe never forgets. This is why, when something seems to forget, physicists get very nervous. Burning a book looks like forgetting, but it is not. The information is just scattered, made impractical to recover, but not actually erased. The same is true of a cup of coffee cooling, a glass shattering, a star fading. Entropy increases, our practical knowledge decreases, but the underlying information persists. To violate that principle would be to violate the bedrock of quantum mechanics itself. It would be to admit that probabilities can leak away, that the universe can simply forget its own past in some deep and final way. Every prediction quantum mechanics has ever made, every laser, every transistor, every piece of modern technology that relies on quantum effects, owes its existence in some sense to unitarity. Throw it out, and physics, as we know it, begins to crumble. The very framework that lets us calculate anything at all, lets us predict the outcomes of experiments, lets us trust the relationship between cause and effect at the deepest level of nature, depends on this principle. To say it is sacred is not an exaggeration. To say it is non-negotiable is barely strong enough. Now imagine throwing that same book into a black hole. The book crosses the event horizon, that boundary in space beyond which not even light can escape, the one-way membrane that defines a black hole as a black hole. And from the perspective of any external observer, it is simply gone. According to the no-hair theorem, a celebrated result in general relativity formalized by John Wheeler, Werner Israel, Brandon Carter, Stephen Hawking, and others in the 1960s and 70s. A black hole can be completely described by just three numbers: its mass, it's an electric charge, its angular momentum or spin. That is it. Wheeler put the idea memorably when he said that black holes have no hair, meaning they have no features that distinguish one from another beyond those three parameters. The phrase, by the way, was apparently considered slightly obscene by Richard Feynman, who objected to its use. But it stuck anyway, becoming one of the most quoted lines in modern physics. Two black holes with the same mass, charge, and spin are identical, even if one formed from the collapse of a massive blue star and the other from the slow accumulation of dust and gas over billions of years. Their pasts are erased. Their identities are stripped down to the barest mathematical skeleton. This was the situation in the early 1970s. Black holes existed in the mathematics of general relativity, having been first discovered as solutions by Karl Schwarzschild in 1916, while he was serving in the German army on the Russian front during the First World War. Schwarzschild, an established astronomer who had volunteered for military service despite being in his early 40s, worked out the implications of Einstein's freshly published general theory of relativity, while suffering from a painful autoimmune disease that would eventually kill him later that same year. He found that a perfectly spherical mass concentrated below a certain radius would create a region of spacetime from which nothing could escape. For decades, this was treated as a mathematical curiosity. the kind of solution that you found interesting on paper, but did not expect to encounter in the real universe. Even Einstein himself, in a 1939 paper, argued that no real physical process could produce such an object. The mathematical singularity at the center of the Schwarzschild solution was, Einstein thought, an artifact of unrealistic assumptions, not a feature of nature. By the 1960s, however, astronomers were beginning to find compelling evidence that such objects actually existed, lurking in the remnants of dead massive stars and at the centers of galaxies. Robert Oppenheimer and his student Hartland Snyder had shown back in 1939, in a paper published the same day Germany invaded Poland, that a sufficiently massive star would inevitably collapse to a singularity once its nuclear fuel ran out. The work was forgotten in the chaos of the war and the Manhattan Project, but in the 1960s, theorists rediscovered it, and astronomers began finding objects in the sky that fit the predictions. The mathematical curiosity was becoming an astronomical fact, but nobody yet thought of them as having any particular relationship to information. They were just simple, smooth, featureless balls of warped spacetime, with the strange property that nothing that crossed their inner boundary could ever return. The trouble was about to begin. It began with a young Israeli-American graduate student named Jacob Bekenstein. Bekenstein had been born in Mexico City in 1947, the son of refugees who had fled Europe during the Second World War. He grew up bilingual, scientifically inclined from childhood, and ended up at Princeton University, where he studied under the legendary John Wheeler, the same Wheeler who had given black holes their name, the same Wheeler whose voracious curiosity had carried physics forward from the era of Einstein to the era of quantum gravity. Bekenstein was working on his doctoral thesis, and he had a peculiar habit of asking questions that nobody else thought to ask. One of those questions concerned the second law of thermodynamics, which says that the total entropy of a closed system can never decrease. Bekenstein worried about what happens to the entropy of a hot cup of tea when you toss it into a black hole. The tea has entropy, a measure of its disorder, of the number of different microscopic ways its molecules could be arranged given its overall macroscopic properties. If you toss it into a black hole and the tea disappears, has that entropy disappeared too? If so, the second law has been violated. The universe is now less disordered than before, in defiance of one of the most reliable laws of physics. Bekenstein refused to accept this. The second law was sacrosanct. There had to be a way to save it, so he proposed something audacious. In his 1972 and 1973 papers, he suggested that the black hole itself must carry entropy, not just a little bit, an enormous amount, enough to absorb the entropy of anything that fell into it, so that the total entropy of the universe, the entropy of the black hole plus the entropy of everything outside it, would never decrease. This would save the second law of thermodynamics from the black hole's appetite. The second law could be promoted to a more general form, sometimes called the generalized second law, which states that the entropy of black holes plus the entropy of everything else can never decrease, providing a unified framework that includes the strange physics of black holes within the broader principles of thermodynamics. But where would that entropy lie? A black hole, supposedly, has no internal structure. It is just mass, charge, and spin. The answer Bekenstein gave was strange and beautiful, and it came partly from a hint provided by Wheeler's other students, and partly from Hawking's own earlier work on black hole mechanics. Bekenstein proposed that the entropy of a black hole is proportional not to its volume, the way you would expect for an ordinary object, but to the surface area of its event horizon. As a black hole swallows more matter, its event horizon grows, and so does its entropy. This was inspired by Hawking's 1971 proof of what is called the area theorem, that the total area of black hole event horizons in any classical process can never decrease, a property strangely reminiscent of the second law of thermodynamics itself. The parallel between the two principles was so striking that Bekenstein suspected it could not be coincidental. The area of an event horizon must, he reasoned, be a measure of something thermodynamically meaningful. It must be a measure of entropy. The connection Bekenstein drew was specific and precise. Each unit of area on the event horizon, measured in tiny squares, each 1 Planck length on a side, corresponds to 1 unit of information. The Planck length is about 10 to the minus 35 meters, far smaller than any subatomic particle. The scale at which the very concept of distance starts to break down, the scale at which quantum gravity is supposed to become important. And on the surface of a black hole, every one of those tiny squares is, in some sense, a single bit. A single yes or no. A single piece of memory. A single elementary unit of stored information. The total information storage capacity of a black hole, in this picture, is given by its surface area divided by 4 times the Planck area, with the factor of 4 eventually pinned down by the precise calculations of black hole thermodynamics. Most physicists, when they first heard this idea, dismissed it. The most prominent skeptic was Stephen Hawking himself. Hawking knew that if a black hole had entropy, then it must also have temperature by the universal laws of thermodynamics. The two go hand in hand. And if it had temperature, it must radiate heat, just as any warm object does. But a black hole, by definition, cannot radiate anything. Nothing escapes a black hole. The whole idea seemed contradictory, an obvious mistake by an inexperienced graduate student who had not thought things through. Hawking set out to prove Bekenstein wrong, to put this entire line of thought to rest, to restore the orderly understanding of black holes that he and his colleagues had carefully constructed. What Hawking discovered instead, in 1974, would shake physics to its foundations. Working through a careful analysis of quantum field theory in the curved spacetime around a black hole, applying the methods of particle physics in a context where they had rarely been applied before, Hawking found that black holes are not, in fact, perfectly black. They emit a faint glow of particles, a thermal radiation, leaking out from just outside their event horizons. The mechanism, in a simplified picture, involves the constant quantum fluctuations of the vacuum, producing virtual particle-antiparticle pairs near the horizon. Normally, these pairs immediately annihilate each other, and the vacuum remains undisturbed. But near a black hole, occasionally one member of the pair falls inside the horizon, while the other escapes outward. The escaping particle has become real, with positive energy, while its partner falls inside, carrying negative energy that effectively reduces the black hole's mass. Over time, the black hole loses mass and emits radiation. The temperature is tiny for any astrophysical black hole. For one with the mass of our Sun, the temperature would be about 60 nanokelvin, far colder than the cosmic microwave background, undetectable by any conceivable instrument with our current technology. But it is not zero, and the implications were enormous. The discovery, published first as a brief 2-page note in the journal Nature with the deliberately provocative title Black Hole Explosions, came as a shock to Hawking himself. He had set out to disprove Bekenstein. Instead, he had given black hole entropy its complete and rigorous foundation. He had derived the precise temperature a black hole must have, an equation now known as the Hawking temperature, which depends inversely on the black hole's mass. He had shown that Bekenstein's intuition was right. The entropy of a black hole really does scale with the area of its horizon, with a specific numerical coefficient, 1/4, in natural units where the Planck constant, the speed of light, and Newton's constant are all set to 1. This formula, now called the Bekenstein-Hawking entropy, is one of the most celebrated equations in all of theoretical physics. It links gravity, thermodynamics, and quantum mechanics in a single, deeply mysterious expression. The mere existence of that equation tells us that black holes have a microscopic structure, some hidden inner machinery of states whose total count is mind-bogglingly enormous. For a black hole the mass of the Sun, the number of possible microscopic states is something like 10 to the 77th power. That is a 1 followed by 77 zeros, more than the number of atoms in a million galaxies, all hidden behind that smooth, featureless event horizon, accessible to no observer, encoded in nobody knew quite what. But the discovery did something else, something that would not become apparent for another year or two. It opened a door to a problem so deep and so distressing that physicists are still wrestling with it half a century later. Because if black holes radiate, then over enormously long timescales, they must lose mass. They must shrink, and eventually, given enough time, much longer than the current age of the universe, but still a finite amount of time, they must evaporate completely. They must vanish. They must disappear. A stellar mass black hole would take something like 10 to the 67th years to fully evaporate. An unimaginable span of time compared to the 14 billion years our universe has existed so far. The cosmic microwave background, currently bathing the universe at a temperature of about 2.7 Kelvin, will eventually cool below the temperature of stellar mass black holes, allowing those black holes to net radiate energy out into the surrounding space. Until that happens, black holes are actually absorbing more cosmic microwave background radiation than they are emitting, so they are still growing on average. But once the universe cools enough, black holes will begin their long, slow evaporation, and the process is real, and it eventually ends with the black hole gone. And when they do disappear, what happens to everything that fell in? This was the question Hawking asked himself in 1975 and 1976, in the years immediately following his discovery. The radiation that pours out of a black hole, he calculated, is purely thermal. It has the same featureless statistical character as the light from any hot object. A campfire and a glowing chunk of iron radiate the same kind of light at the same temperature, even though one was once a tree, and the other was once an ore drawn from beneath the earth. The thermal radiation carries no memory of what produced it. The fact that black-body radiation looks the same regardless of what is producing it had long been a familiar observation. And indeed, Max Planck's 1900 derivation of the black-body radiation spectrum had been the seed from which the entire quantum revolution had grown. But now Hawking was applying this venerable result to a deeply weird situation. Imagine a black hole formed from the collapse of a particular star with all its unique features, its chemical composition, the precise arrangement of its atoms, perhaps a small spaceship orbiting in its outer atmosphere when the collapse began, perhaps an entire planet falling in during the late stages of the explosion. All of that information is gone, hidden inside the event horizon. As the black hole slowly evaporates over an unimaginable span of time, it emits Hawking radiation that, according to Hawking's calculations, knows nothing about any of it. The radiation is thermal. It carries no trace of the star, the spaceship, the planet, or anything else. So when the black hole finally disappears, what is left? Just an outgoing cloud of featureless radiation. The information that went in is not in the radiation. It is not in the black hole because the black hole is gone. It is not hiding anywhere. It is, as far as anyone can tell, simply destroyed. This was Hawking's conclusion, presented forcefully in his 1976 paper called The Breakdown of Predictability in Gravitational Collapse. Information, he argued, can be lost. Pure quantum states, which describe systems with complete information, can evolve into mixed states, which describe systems where some information is permanently inaccessible. The fundamental principle of unitarity, the bedrock of quantum mechanics, is violated by black holes. This was not a minor technical claim. This was a sweeping revision of physics. Hawking proposed that the very rules of quantum mechanics needed to be modified to accommodate gravity, and that black holes were the laboratory where this revision became visible. He even sketched out, in subsequent work, some modified mathematical structures that he thought might replace ordinary quantum mechanics in a universe with black holes. The dollar matrix, he called one such structure, generalizing the S-matrix of ordinary quantum field theory in a way that allowed for the kind of pure-mixed evolution that his calculations seemed to require. This conclusion was a hand grenade thrown into the foundations of physics. Most physicists at the time either ignored it or quietly hoped it would go away. A few took it seriously and accepted that quantum mechanics might need to be modified, but two physicists in particular found Hawking's claim utterly unacceptable, and they were prepared to spend decades fighting it. Their names were Gerard 't Hooft, a Dutch theorist who would go on to win the Nobel Prize for his work on the foundations of the Standard Model of particle physics, and Leonard Susskind, an American whose path into physics had begun rather improbably as a plumber's apprentice in the Bronx, before he eventually made his way into the academic world. Susskind has described, in interviews, and in his book The Black Hole War, the moment he first heard Hawking present these ideas at a small conference in 1981, held in the basement of Werner Erhard's mansion in San Francisco. Erhard was the founder of a controversial self-help movement called EST, but he was also a wealthy enthusiast for theoretical physics, who occasionally hosted small gatherings of leading thinkers. Hawking, with characteristic confidence, had laid out his argument and concluded that the conservation of information must fail. Susskind sat there feeling, in his own words, that the foundation of his life's work had just been knocked out from under him. To accept Hawking's conclusion was to give up on the idea that physics is a deterministic, unitary, time-reversible affair at its deepest level. It was to admit that the universe could simply lose track of its own history. Susskind refused. He went home, he started thinking, and over the next 20 years he would lead a counteroffensive that would transform our understanding of black holes, of gravity, and ultimately of space and time themselves. 't Hooft, working independently, would arrive at many similar ideas, sometimes earlier than Susskind, and his contributions to the eventual resolution would be just as central. The struggle between Hawking on one side and Susskind, and 't Hooft on the other, would last decades, and would draw in nearly every theoretical physicist working on quantum gravity, fundamentally reshaping the field along the way. The first serious move in that counteroffensive came in 1993, when Susskind, together with his collaborators Lars Thorlacius and John Uglum, proposed a radical and seemingly contradictory idea called black hole complementarity. The setup of the paradox went something like this. Imagine a friend of yours, call her Alice, falling into a very large black hole. Large enough that the tidal forces near the event horizon are gentle, large enough that the curvature of spacetime at the horizon is small in any local measurement. From your perspective, watching from a safe distance outside, Alice never quite reaches the event horizon. Her descent slows as she approaches it, an effect of the gravitational time dilation that becomes ever more extreme near the horizon. Her image redshifts. Her clock appears to tick more and more slowly, until eventually she is frozen at the horizon, her image fading to invisibility as the photons she emits are stretched into longer and longer wavelengths. From your perspective, Alice and everything she carries, including all the information that defines her, gets smeared out across the surface of the black hole, encoded in the structure of the horizon itself. Eventually, as the black hole evaporates over cosmic ages, this information is released back into the universe through the Hawking radiation. But from Alice's own perspective, something completely different happens. According to Einstein's equivalence principle, the cornerstone of general relativity, Alice should notice nothing special as she crosses the event horizon of a sufficiently large black hole. The horizon is not a physical surface in the usual sense. It is just a coordinate boundary, a place defined by the property that nothing can cross it in the outgoing direction. But locally, there is nothing dramatic happening. Alice should sail through it smoothly, continue inward, and eventually meet her doom at the singularity at the center, where the tidal forces finally tear her apart on her way to the infinitely curved point at the heart of the black hole. From her perspective, the information that defines her remains inside her body until the bitter end. So which is it? Is the information smeared on the event horizon and eventually radiated out, or is it carried inside with Alice to the singularity? It cannot be both, because that would violate the no-cloning theorem of quantum mechanics, which forbids the duplication of arbitrary quantum information. The no-cloning theorem, established by William Wouters and Wojciech in 1982, is itself a consequence of unitarity, and so a violation of no-cloning would be just as fatal to quantum mechanics as the original information loss problem. And yet both descriptions seem to be required by the structure of the situation. Alice clearly experiences something definite, and outside observers clearly measure something definite. How can these two definite things contradict each other? Suskind's resolution was bold. He proposed that the two descriptions are not contradictory because no single observer can ever see both at once. Alice cannot send a signal back out of the black hole to inform an outside observer that she is fine. An outside observer cannot follow Alice in without becoming an inside observer, at which point they too are causally disconnected from the rest of the universe. The information is duplicated in a sense, but the duplication is invisible. There is no single perspective from which the contradiction can be detected. The two descriptions are complementary, like the wave and particle descriptions of an electron in old-school quantum mechanics. You use one or the other depending on the question you are asking, and you never use both at once. To experimentally probe the supposed contradiction would require a single observer to gather all the relevant data, and the geometry of spacetime simply does not allow such an observer to exist. The very impossibility of detecting the contradiction is what allows the universe to get away with both descriptions being true in their respective contexts. To make this work, Susskind introduced the idea of the stretched horizon, a kind of imaginary surface located just outside the true event horizon of the black hole. Separated from it, by about 1 Planck length. This stretched horizon, from the outside observer's perspective, behaves like a hot, dynamic, membrane-like surface, absorbing infalling matter, scrambling its information, and eventually radiating it back out. The information is preserved. It is just stored, temporarily, on this hot quantum membrane that sits at the edge of the black hole. To Alice, falling in, the stretched horizon does not exist as a physical object. For her, there is nothing remarkable at all about the horizon region, just smooth, gently curved spacetime that she passes through without incident. But to outside observers tracking the black hole's evolution, the stretched horizon is the place where the information lives. It is the place where the universe writes down what is happening before sending it back, eventually, into the surrounding cosmos. This was a revolutionary suggestion, but it raised an obvious question. How much information can the stretched horizon hold? The answer, Susskind realized, was exactly the Bekenstein-Hawking entropy. Every Planck-sized patch of the horizon can store 1 bit. The total number of bits that a black hole can encode is precisely the area of its event horizon divided by 4 times the Planck area. The information capacity of a region of space, in other words, scales with area, not volume. Take a moment to let that sink in. Take a chunk of space the size of a basketball. Now take a chunk twice as big in every direction. Ordinary intuition says the bigger chunk can hold 8 times as much stuff because volume scales with the cube of the linear dimension. But for the maximum amount of information you can squeeze into that region before you make a black hole, the scaling is only with the square of the linear dimension. The bigger chunk only holds 4 times as much information. There is a deep mismatch between volume and information, and the information is somehow tied to surfaces, not interiors. This is an extraordinary statement. In ordinary physics, the amount of stuff you can fit into a box scales with the volume of the box. Double the size of the box in every direction, and you can fit 8 times as many balls inside it. But for a black hole, and Susskind began to suspect, for any region of space, the information capacity scales with the surface area, not the volume. Double the size of the region, and you only get 4 times the information capacity, not 8. The information seems to live on the boundary, not inside. The interior, in some sense, contains no more information than its surface does. There is something profoundly strange about how reality is organized. Something that goes against every common-sense intuition we have about how stuff is supposed to work. In 1993, Gerard T. Hooft had already pushed this observation toward an even more radical idea. In a speculative paper called Dimensional Reduction in Quantum Gravity, T. Hooft proposed that the entire description of any region of space might be encoded on its boundary. The 3-dimensional world we appear to inhabit, with its volumes and its depths, might in fact be a kind of projection from a 2-dimensional surface. A hologram, in the technical sense of the word, borrowed from the science of holography, where 3-dimensional images are reconstructed from interference patterns recorded on 2-dimensional plates. Susskind picked up this idea and championed it, giving it a name that has stuck ever since: the holographic principle. He developed it further in a series of papers throughout the mid-1990s, arguing forcefully that this was not just a curiosity, but a deep statement about the nature of space and the nature of gravity. The holographic principle is one of the strangest claims in modern physics, and yet it has steadily accumulated evidence and respect over the past 3 decades. It says, roughly, that the maximum number of degrees of freedom in any region of space is bounded by the area of the region's boundary in Planck units, divided by 4. Inside that region, all the apparent three-dimensional richness, the atoms, the people, the rooms, the galaxies, is reducible to information encoded on the two-dimensional boundary. The third dimension, the depth, is in some sense an illusion or an emergent property. The way a holographic image on a credit card creates the illusion of three-dimensionality from patterns etched onto a flat piece of plastic. The room you are sitting in right now, if the holographic principle is correct, contains no more information than could be written on its walls. You yourself, every memory in your brain, every cell in your body, every quark inside every atom, are in some deep sense reducible to a pattern on a two-dimensional surface. The richness of the three-dimensional world is, in some precise sense, a kind of optical illusion produced by a more fundamental two-dimensional reality. Applied to a black hole, the holographic principle says something stunning. The interior of a black hole, the region behind the event horizon, including whatever fell in, including all the matter heading toward the singularity, does not have any independent existence. Everything that fell in is fully described, in some other language, by patterns of quantum information on the surface of the event horizon. The black hole is not a three-dimensional object with a vast and mysterious interior. It is a two-dimensional surface that gives rise, through the mathematics of holography, to the appearance of an interior. And on that surface, written in some language nobody yet understands, is every memory of everything that ever fell in. This is the sense in which black holes can be thought of as cosmic memory. Not metaphorically, but quite literally. Every piece of information that crosses the event horizon is encoded on the surface, with a density of 1 bit per Planck area. A black hole the size of the Sun has an event horizon of about 37,000 square kilometers. Translated into bits, that comes out to roughly 10 to the 77th bits of information. Vastly more storage capacity than every digital device ever made by humanity combined. Vastly more than the total information content of every book ever written, every conversation ever had, every photograph ever taken, every song ever recorded, every email ever sent. And that is just one stellar mass black hole. The supermassive black hole at the center of our Milky Way galaxy, Sagittarius A star, with a mass of about 4 million suns, holds something like 10 to the 90th bits. The supermassive black holes at the centers of larger galaxies, with masses reaching tens of billions of suns, hold even more. Considered as memory devices, these objects beggar the imagination. They are storage facilities the likes of which our species, with its rapidly expanding archives of digital memory, can scarcely conceive. To put it in perspective, the total estimated digital storage capacity of humanity in the early 2020s was around something like 10 to the 22nd bits. A single stellar mass black hole carries information storage capacity that exceeds this by something like 55 orders of magnitude. The cosmic libraries dwarf everything we have ever built, but the holographic principle was, in its early years, more of a slogan than a precise theory. It needed an actual working example. It needed a concrete case where you could show, mathematically, that a higher dimensional gravitational theory really was equivalent to a lower dimensional non-gravitational theory living on its boundary. That example came in late 1997 from a young Argentinian-American physicist named Juan Maldacena. Maldacena was working at Harvard at the time, just out of graduate school at Princeton, and he was investigating certain configurations in string theory. He was 29 years old, and he was about to publish what would become the most cited paper in theoretical physics. String theory, the leading candidate for a theory of quantum gravity, replaces the point particles of standard physics with tiny, vibrating strings, whose modes of vibration produce the various particles we observe. By studying particular arrangements of strings and branes, higher dimensional objects that strings can end on, Maldacena discovered a remarkable mathematical equivalence. A particular gravitational theory living in a five-dimensional spacetime called anti-de Sitter turned out to be exactly equivalent to a particular non-gravitational quantum field theory living on the four-dimensional boundary of that space. The two theories were not similar. They were not analogous. They were the same theory, expressed in two completely different languages. Every gravitational phenomenon in the higher dimensional bulk had a precise translation into some non-gravitational phenomenon on the boundary, and vice versa. This was the ADS/CFT correspondence, anti-de Sitter/conformal field theory correspondence. It was, and remains, the most concrete realization of the holographic principle. It is a precise, mathematically tractable example of holography at work, and it has been cross-checked in thousands of ways since Maldacena's original paper. The implications were immediate and enormous. If you wanted to understand what happens in a region of space containing gravity, including what happens inside a black hole, you could, in principle, just look at the boundary. The boundary contains everything. The interior is fully determined by the patterns of quantum field theory on the surface, with no extra information needed and no extra information possible. The development of ADS/CFT was extended and refined by other physicists in the years immediately following Maldacena's original paper. Edward Witten, of the Institute for Advanced Study, perhaps the most influential mathematical physicist of his generation, wrote a foundational paper in early 1998 that pinned down many of the technical details. Stephen Gubser, Igor Klebanov, and Alexander Polyakov developed an explicit dictionary translating between the two sides of the correspondence. By the end of the 20th century, ADS/CFT was rapidly transforming theoretical physics, providing new tools for studying quantum gravity, strongly coupled gauge theories, and condensed matter physics. The correspondence has been applied to problems ranging from the dynamics of quark-gluon plasmas produced in heavy ion collisions to the behavior of strongly correlated electron systems in solid-state physics. It is one of the most fruitful ideas in modern theoretical physics, and it all started as an attempt to make precise the relationship between black holes and information. In the ADS/CFT framework, a black hole in the gravitational bulk corresponds to a hot soup of particles in the boundary field theory. The hot soup is a perfectly ordinary quantum system, evolving according to the perfectly ordinary, perfectly unitary rules of quantum mechanics. Information is conserved on the boundary, because the boundary theory is just a conformal field theory of the kind physicists understand quite well. And if information is conserved on the boundary, and the two theories are equivalent, then information must also be conserved in the bulk. Hawking's information loss conclusion in the ADS/CFT context simply could not be correct. There had to be a way for the information to come out. The boundary theory left no room for forgetting, and so the bulk theory, which is the same theory in a different language, must also leave no room for forgetting. By the late 1990s and early 2000s, this was becoming the consensus among string theorists. The holographic principle, plus ADS/CFT, gave a strong indirect argument that black holes do not destroy information. The hidden mechanism by which Hawking radiation preserves information was still mysterious. Nobody could point to exactly how a thermal-looking spectrum carries the imprint of what fell in, but the existence of such a mechanism seemed mathematically guaranteed. The argument was something like a proof by contradiction. Assume information is lost in black holes, then unitarity is violated in the bulk gravitational theory. But the bulk theory is dual to a boundary theory in which unitarity manifestly holds. Therefore, information is not lost. The conclusion was airtight, even if the underlying mechanism remained obscure. Hawking himself eventually came around. In 2004, at a conference in Dublin, the 17th International Conference on General Relativity and Gravitation, he publicly conceded his 30-year position. He announced that he had been wrong, that information is not lost in black holes after all. He gave a talk in which he sketched an argument for how the information could be preserved through subtle correlations in the Hawking radiation. Although the technical details he provided did not fully convince everyone in the audience. Famously, this conceded an old bet he had made in 1997 with the physicist John Preskill of Caltech, who had insisted all along that information must be preserved. The terms of the bet specified that the loser would buy the winner an encyclopedia, from which information could easily be retrieved. Hawking handed Preskill a baseball encyclopedia, called the Total Baseball Encyclopedia in some accounts, from which Preskill could supposedly easily extract information about any baseball player in history. Hawking, with his customary wry humor, suggested it might have been more fitting to burn the encyclopedia first and hand over the ashes, since the ashes also technically still contain all the information, just in scrambled form that nobody could ever practically recover. Preskill was not entirely satisfied, since he had wanted the British equivalent, but he accepted the bet. But even as Hawking conceded, the deeper problem had not actually been solved. ADS/CFT told us that information must be preserved, but it did not tell us how. The actual mechanism by which Hawking radiation carries information out of a black hole, the precise way in which the past is stored on the horizon and then handed back to the universe, remained obscure. We had proof that the answer existed, but we did not have the answer. And in the 2000s and 2010s, attempts to work out the details would lead to crises, paradoxes, and breakthroughs that nobody saw coming. The first major step toward making the picture more concrete came from a quiet, careful Canadian physicist named Don Page. Page had been one of Hawking's students in the 1970s, working under him at Caltech, and then continuing the collaboration when both moved to Cambridge. He had been there for many of the early discussions of the information paradox, and unlike Hawking, he had always believed that information must be conserved. Page was a deeply religious man, an evangelical Christian, and his commitment to information conservation seemed to draw from someplace even deeper than physics, a conviction that the universe is the kind of place where things matter, where histories are real, where the past genuinely happened. In 1993, Page published a paper that asked a question of profound simplicity. If a black hole really does preserve information, what does that look like over time? How does the entanglement between the black hole and the Hawking radiation evolve as the black hole evaporates? To answer this, Page made a single, powerful assumption. He assumed that the radiation coming out of the black hole is what physicists call a random pure state, a state drawn at random from the Hilbert space of pure states, not a thermal state, but a state that looks thermal when you only have access to part of it. He then asked what the entanglement entropy, a precise measure of how correlated the radiation is with whatever is left of the black hole, should do over time? The answer was strikingly simple. In the early stages of evaporation, when the black hole is large and the radiation is small, the entanglement entropy of the radiation grows. The early Hawking particles are entangled with the black hole, and as more of them are emitted, the entanglement increases. So far, this matches Hawking's original calculation. But Page showed that this growth cannot continue forever. The total entanglement entropy is bounded by the smaller of two numbers: the entropy of the radiation or the Bekenstein-Hawking entropy of the remaining black hole. At first, the radiation is small, so its entropy bounds the entanglement. But as the black hole shrinks, eventually it becomes a smaller system. From that moment on, called the Page time, the entanglement entropy must turn around and start decreasing. It must follow a curve, the Page curve, as it became known, that rises from zero, peaks at roughly the halfway point of evaporation, and falls back to zero as the black hole disappears entirely. If the Page curve is correct, then information starts coming out of the black hole halfway through its lifetime. The early Hawking radiation is essentially random and carries no recoverable information. But starting at the Page time, the later radiation must be precisely correlated with the earlier radiation in just such a way that, when you eventually have all of it, you can, in principle, reconstruct everything that ever fell in. The radiation is not just random thermal noise. It is, in some subtle and intricate way, a coded message, a vast, scrambled message that contains within its structure every detail of every star, every spaceship, every planet, every grain of dust that ever fell into the black hole. The thermal appearance is a kind of disguise, hiding the underlying structure from any observer who only looks at part of the radiation. Only by gathering all of it, every photon, every neutrino, every particle that escaped the black hole over its entire evaporation history, could you decode the message and recover the information. This was a beautiful prediction. But for decades, nobody knew how to actually derive the Page curve from a real calculation in gravity. Hawking's original derivation gave a curve that just kept rising, in flat contradiction to Page's prediction. The Page curve was what unitarity demanded, but no one could show that it actually emerged from the equations of physics. Something was missing. Some new ingredient, some piece of the puzzle that nobody had thought of. The conviction that the Page curve must be right grew stronger over the years, supported by every theoretical argument, every consistency check from ADS/CFT, every refinement of holographic thinking. But the actual derivation remained out of reach. The Page curve became something like the holy grail of black hole physics, a precise prediction that everyone believed had to be correct, but that no one knew how to actually establish from first principles. Then, in 2012, a new paradox erupted that made the whole problem look worse than ever. Four physicists, Ahmed Almeri, Donald Marolf, Joseph Polchinski, and James Sully, often referred to collectively by the initials AMPS, published a paper that pointed out what looked like a fatal inconsistency in everyone's picture. Their argument went like this: if black holes preserve information, as everyone now believes, then the later Hawking radiation must be highly entangled with the earlier Hawking radiation. This is just what the Page curve demands. The information stored in the radiation is encoded in subtle correlations across the entire output. And after the Page time, those correlations become essential. But it is a basic fact of quantum mechanics that a particle cannot be highly entangled with two different things at the same time, a constraint called the monogamy of entanglement. The newly emitted Hawking particles are also supposed to be entangled with their partners, just inside the black hole horizon. That is what makes the horizon smooth for an infalling observer like Alice, what makes the vacuum near the horizon look like an ordinary vacuum from her perspective. If they are entangled with the early radiation, they cannot also be entangled with their interior partners, and vice versa. Something had to give. AMPS argued that the most conservative resolution was to give up the assumption that the horizon is smooth for an infalling observer. Instead, they proposed that as a black hole ages, the entanglement structure required for information preservation creates a wall of high-energy quanta sitting just inside the event horizon. They called it a firewall. An infalling observer would not, contrary to Einstein's equivalence principle, sail smoothly through the horizon. They would slam into the firewall and be incinerated, burning up in a sheet of intense radiation. The interior of the black hole in this picture is not the gentle place that classical general relativity describes. Crossing the event horizon is not a non-event. It is the end. Alice does not pass smoothly into the interior. She is annihilated in a wall of fire at the moment of crossing. The firewall paradox sent the physics community into a fresh round of crisis. To accept firewalls was to abandon the equivalence principle, one of the most cherished ideas in general relativity, the foundation on which Einstein had built his entire theory of gravity. To reject firewalls was to abandon either unitarity or quantum field theory near the horizon, or some other equally cherished assumption. Almost every plausible resolution required giving up something that physicists did not want to give up. The 2012 and 2013 physics literature is filled with proposals, counterproposals, increasingly elaborate thought experiments, and a sense of bewildered urgency. Black hole complementarity, which had seemed to settle the question 2 decades earlier, was suddenly in doubt. Workshops and conferences were organized around the firewall problem. Senior physicists who had thought the information paradox was essentially solved found themselves embroiled in a fresh debate that no one knew how to settle. It was widely felt that something fundamental had been missed, that some new piece of physics was needed to resolve the tension between unitarity, the equivalence principle, and the monogamy of entanglement. In the middle of this crisis, Juan Maldacena and Leonard Susskind proposed an idea so audacious that it took even other physicists years to digest. They called it ER equals EPR, a slogan that elegantly equates two seemingly unrelated phenomena. ER stands for Einstein-Rosen, referring to the wormholes that Einstein and Nathan Rosen had described in their 1935 paper as bridges connecting two regions of spacetime. EPR stands for Einstein-Podolsky-Rosen, referring to the quantum entanglement that Einstein, Boris Podolsky, and Nathan Rosen had analyzed in another famous paper from the same year. Two completely different ideas from two different parts of physics, but sharing two of the same authors. Maldacena and Susskind proposed that they are, secretly, the same thing. The conjecture says that whenever two quantum systems are entangled, they are connected, in some sense, by a wormhole. Two entangled black holes are connected by a wormhole through space, a non-traversable Einstein-Rosen bridge that links their interiors. Two entangled particles are connected by a tiny, microscopic version of the same thing. Entanglement, the most quintessentially quantum phenomenon, is the same thing as geometry, spooky action at a distance, as Einstein called it disparagingly, is actually mediated by an invisible network of tiny wormholes weaving through spacetime. If ER equals EPR is correct, then the firewall paradox dissolves. The newly emitted Hawking particles are entangled with the early radiation, yes, but that entanglement is implemented through a wormhole that connects them. The interior of the black hole and the early radiation are, in a sense, the same place, connected by wormholes. There is no need for a firewall, because the entanglement structure that was supposed to demand one is actually a geometric feature of the spacetime itself. The monogamy of entanglement is not violated, because what looked like two separate things, the interior partner of the new Hawking particle and the early radiation, are really the same thing in disguise, connected by a wormhole that makes them effectively identical. The apparent paradox arose from treating these as two independent systems, when in fact, they are geometrically the same system viewed from two different angles. This idea, beautiful and strange, and not yet rigorously proven, suggests something profound about the nature of space. Space, it seems, may not be a fundamental ingredient of reality at all. Space may be built out of entanglement. The web of quantum correlations between systems may be the very thing that sews the universe together into a connected whole. Mark van Ramstonk, a Canadian physicist at the University of British Columbia, had explored a related idea in 2010 in a paper that took some years to gain attention, but is now seen as foundational. Van Ramstonk showed that if you imagine systematically reducing the entanglement between two regions in an ADS/CFT setup, the geometry connecting them literally pulls apart. The two regions become geometrically separate. Take away all the entanglement, and the universe atomizes into disconnected pieces. The geometry of space, in this picture, is not prior to the quantum correlations between its parts. The geometry is built up out of those correlations. Spacetime emerges from entanglement. This is a profoundly strange idea. The smooth, three-dimensional space we move through in our daily lives, the space in which planets orbit and galaxies rotate, the space in which light travels and gravity propagates, may not be a fundamental feature of the universe at all. It may be a structure that emerges, in some not yet fully understood way, from a web of quantum correlations that exists at some deeper level. Reduce those correlations, and space itself starts to fall apart. Build up the right correlations, and you can build up a region of space with all its geometric features. The universe, in this picture, is fundamentally about information and its correlations, and space is a derived concept, a useful way of organizing those correlations into something that looks geometric. So when we ask how a black hole stores information, the answer that has slowly emerged is this. The information is stored as patterns of entanglement, and those patterns are equivalent to a geometric structure, a web of microscopic wormholes that extends through the event horizon and connects the interior to the exterior. The black hole in this picture is not a destroyer of information, but a vast, interconnected memory whose state is encoded simultaneously in its surface, in its interior, and in the radiation streaming out of it. Multiple equivalent descriptions of the same underlying reality related to each other by the deep mathematics of holography. Pick any description you like, and you find the information present, encoded in its own way, ready to be read by anyone clever enough to know the language. But the firewall paradox refused to die quickly, and other proposals kept appearing. In 2016, Stephen Hawking himself, together with Malcolm Perry of Cambridge and Andrew Strominger of Harvard, published a paper called Soft Hair on Black Holes. The paper revisited the old no-hair theorem and pointed out that the theorem applies only to certain kinds of features. It says that black holes have no hard hair, no observable distinguishing features at finite energy. But Hawking, Perry, and Strominger argued that black holes can have soft hair, low-energy excitations of the gravitational and electromagnetic fields that encode information about everything that fell in. These soft-hair degrees of freedom live on the horizon and are associated with an infinite family of symmetries called BMS supertranslations, named after Hermann Bondi, Mark van der Berg, Arthur Metzner, and Rainer Sachs, who studied them in the 1960s. The BMS supertranslations had been a known feature of asymptotically flat spacetimes for decades, but their relevance to black hole information had not been fully appreciated until Hawking and his collaborators connected the dots. The idea is subtle. When something falls into a black hole, it leaves a permanent imprint on the gravitational field at infinity, a memory effect in technical language. The memory effect describes how a passing gravitational wave permanently alters the relative positions of distant test particles, leaving them slightly displaced from where they would otherwise have been. This memory effect can be thought of as a soft graviton, a low-energy gravitational ripple, and the black hole carries a record of every such soft graviton it has ever emitted or absorbed. The full set of these records constitutes the soft hair, and in principle, the soft hair contains enough information to reconstruct what fell in. The information is not stored only on the surface of the black hole, but also in the surrounding gravitational field, encoded in patterns of arbitrarily low energy that nevertheless persist for arbitrarily long times. The soft hair proposal was controversial. Some physicists argued that it did not actually carry enough information to solve the paradox, and others questioned whether the proposal really evades the standard arguments for information loss. Mehrdad Mirbabey and Massimo Porrati published a paper just months after the original soft hair paper, arguing that the soft hair could be removed by an appropriate redefinition of states, and so could not really be doing the work of carrying information. Other physicists pushed back, arguing that the proposal still contained important physics even if it needed refinement. Subsequent work refined the picture, with Sabrina Pasterski and Herman Verland, among others, showing how soft hair can dissolve the firewall problem in certain limits. The debate continues, with new papers appearing every year exploring different aspects of the BMS symmetries and their relation to the information paradox. But the soft hair idea contributed an important new perspective. Black holes really do carry detailed information about their pasts, written in subtle features of the surrounding gravitational and electromagnetic fields. The no-hair theorem, in its classical form, is incomplete. Quantum mechanics, properly accounted for, gives black holes a kind of soft, low-energy memory that classical physics misses. The soft hair work was also notable as one of Hawking's final major contributions to physics. He died in March of 2018, 2 years after the original soft hair paper was published. In the months before his death, he and his collaborators were working on further developments of these ideas, exploring how the soft hair connects to a quantity called supertranslation charge, and how the conservation of these charges constrains the radiation that black holes can emit. There is a kind of poignant elegance in the fact that one of his last major projects was an attempt to solve the very paradox he had started 50 years earlier. The man who had introduced information loss as a serious problem in physics was, at the end of his life, contributing to its resolution. Around the same time, another approach to the information paradox was being developed by the string theorist Samir Mather at Ohio State University. Mather had been working on the problem since the late 1990s, building on earlier work that he and others had done, counting microstates of certain special black holes in string theory. He had reached a radical conclusion. In his picture, the the standard image of a black hole, a featureless event horizon surrounding an empty interior leading to a central singularity, is just wrong. According to Mather, black holes are not empty inside at all. They are filled, all the way out to the event horizon, with a tangled mess of strings and other string theory objects. He calls them fuzzballs. A fuzzball is, in some sense, the literal physical realization of all those microstates that Bekenstein and Hawking counted. The Bekenstein-Hawking entropy says that a stellar mass black hole has something like 10 to the 77th microstates. In the standard picture, those microstates are mysterious and inaccessible. They describe possible interior configurations of a black hole, but the interior is hidden behind the event horizon and cannot, in principle, be probed by outside measurements. In the fuzzball picture, each microstate is a specific, distinct arrangement of strings and brains filling the interior, with no smooth horizon and no singularity. The famous singularity at the center of a Schwarzschild black hole in the fuzzball picture simply does not exist. Neither does the event horizon, at least not as a sharp mathematical surface. Different fuzzballs differ in their internal structure, even though they look the same from far away. They have the same mass, the same charge, the same spin, but they differ in the details of their string configurations. When you toss something into a fuzzball, it does not pass through any event horizon because there is no event horizon, just a fuzzy surface where the strings and brains begin. The infalling object becomes part of the fuzzball structure, adding its own complications to the tangle. And when the fuzzball radiates, the radiation carries detailed information about that structure, just as the light from a glowing star carries detailed information about the star's composition. The Hawking radiation in this picture is not the thermal radiation that Hawking originally calculated. It is the radiation of a complicated, structured object, and that radiation contains within it a precise record of every detail of everything that ever fell in. The information is not preserved through some mysterious mechanism we cannot see. The information is preserved because there was never anything to lose. The fuzzball is just a hot, complicated object, like a star, and it radiates the way stars radiate, with all the spectral features that ordinary objects have. Mather's fuzzball picture is hard to verify in full generality, because constructing explicit fuzzball solutions is mathematically demanding. The interior of a black hole is, even in this picture, a place of extraordinary complexity, and writing down explicit solutions describing every microstate is beyond current mathematical capability. But for certain special types of black holes, particularly those carrying multiple charges in string theory, such as the so-called D1-D5 system that Mather and others have studied in detail, fuzzball solutions have been constructed, and their entropy has been calculated. Remarkably, the counting agrees with the Bekenstein-Hawking entropy. Andrew Strominger and Kamran Vafa had achieved a related milestone in 1996, when they showed that the entropy of certain extremal black holes in string theory could be reproduced by counting the microstates of the corresponding D-brane configurations. This was a landmark result, the first demonstration that the Bekenstein-Hawking entropy formula could be derived from an underlying microscopic theory. Strominger and Vafa were able to count the precise number of string configurations that gave rise to a black hole with given mass and charges, and the number they got agreed exactly with the prediction of the Bekenstein-Hawking formula. This was, and remains, one of the most successful tests of any theory of quantum gravity, and it provided strong evidence that the entropy of black holes really does reflect an underlying microscopic count of distinct quantum states. The fuzzball program, alongside related work on what are called microstate geometries, has provided some of the most direct evidence that black hole information is encoded in genuine quantum states, not lost. Iosif Bena, Emil Martinic, Nicholas Warner, and others have collaborated with Mather over many years to develop ever more sophisticated fuzzball constructions. The program continues to produce new results, with recent papers extending the construction to more complex black holes and exploring the observational signatures that fuzzballs might produce. If real astrophysical black holes are actually fuzzballs, they might produce subtle deviations from the predictions of pure general relativity, deviations that could potentially be observed in gravitational wave signals or in images from instruments like the Event Horizon Telescope. Searches for these deviations are ongoing, with no clear positive detections yet, but with the precision of measurements improving steadily. So by the late 2010s, the situation was something like this. Multiple lines of evidence, holography, ADS/CFT, ER equals EPR, soft hair, fuzzballs, microstate counting in string theory, all pointed in the same direction. Information is preserved. Black holes store memory. The details remained contested. The precise mechanisms differed between different proposals, but the conclusion was becoming inescapable. What was still missing was a clean calculation, a calculation that started from the fundamental rules of gravity and quantum mechanics and produced, as output, the Page curve, the curve that Don Page had argued for in 1993, but that nobody had actually derived from first principles. Every theoretical framework agreed that it had to be there. Every consistency argument insisted it had to be there. But the actual gravitational calculation always seemed to fall just short. That calculation finally arrived, in pieces, between 2019 and 2020. Multiple groups of physicists, working in parallel, made the breakthrough. The key new ingredient was something called a quantum extremal surface, combined with a strange and counterintuitive idea called an entanglement island. The work was led by Ahmed Almeri, Netta Engelhardt, Don Marolf, Henry Maxfield, Jeff Pennington, and others, building on earlier ideas about how to compute entropy in gravitational systems using the Ryu-Takayanagi formula, named after Shinsei Ryu and Tadashi Takayanagi, who in 2006 had given a beautiful prescription for computing entanglement entropy in the ADS/CFT correspondence. By finding the area of a special minimal surface in the bulk geometry. The idea is technical, but the upshot is beautifully strange. When you compute the entanglement entropy of the Hawking radiation properly, taking into account all the contributions from gravity, you find that at early times the entropy grows as Hawking originally calculated. The familiar story holds. But at the Page time, a new kind of contribution becomes dominant, a contribution that comes from a region of spacetime hiding inside the black hole, called an island. The island sits just inside the event horizon, and it carries information that is effectively also encoded in the Hawking radiation outside, through the same wormhole-like entanglement structure that ER equals EPR had hinted at. When you include the island contribution, the entanglement entropy stops growing and starts decreasing, tracing out exactly the Page curve. In other words, after the Page time, the interior of the black hole and the exterior radiation are no longer independent. Through the magic of entanglement and gravitational quantum mechanics, the island region is effectively also part of the radiation. The information that was supposedly trapped inside the black hole has, in a precise mathematical sense, become accessible from outside. The page curve is recovered. Unitarity is preserved. Information comes out. The calculations were technical and involved a tool called the replica trick, which involves taking copies of the spacetime and gluing them together in particular ways, and the resulting geometries are sometimes called replica wormholes. Despite the abstract nature of the mathematics, the conclusion was robust and was checked from multiple angles by multiple groups. This breakthrough, which has been refined and extended in dozens of papers since 2019, is widely considered one of the most important advances in theoretical physics of recent years. It does not yet solve every problem. There are still questions about how the islands work in our own universe, which is not anti de Sitter, and about the detailed mechanism by which information is actually encoded in the radiation. The original calculations were done in highly idealized models, often in two-dimensional gravity rather than the four-dimensional gravity of our world. But the basic idea that islands appear, that they carry information, that they make the page curve emerge, has been generalized to higher dimensions and to more realistic settings. The picture has held up. The mechanism, while still mysterious in some ways, is increasingly tangible and concrete. Physicists can now point to specific equations, specific calculations, that demonstrate how information leaks out of a black hole as it evaporates. What does all of this mean for the way we think about black holes? It means that they are not, as Hawking originally feared, perfect erasers of cosmic history. They are far stranger than that. They are vast, holographic memory devices, places where information is concentrated to a density so extreme that the very geometry of spacetime is reorganized around it. Every atom of every object that ever fell in is recorded somewhere. On the surface, in the soft hair, in the entanglement structure of the Hawking radiation, in the fuzzy strings of the fuzzball interior. The recording is dense, scrambled, and encoded in a language we are only beginning to learn, but it is real. The universe does not forget what falls into a black hole. It just rearranges the record. This conclusion has implications that extend far beyond the technical details of black hole physics. It suggests that the basic principle of information conservation, the bedrock principle of unitarity, holds up even in the most extreme gravitational situations the universe can produce. There is no place in physics where information is permanently destroyed. Black holes scramble it, hide it, encode it in ways that may take longer than the age of the universe to unscramble, but they do not destroy it. The cosmos is a place of perfect, if often impractical, memory. It also suggests something profound about the nature of space and time. The holographic principle, ER equals EPR, the island formula, these are all hints that the smooth, three-dimensional space we experience is emergent, that it bubbles up from a deeper, more primitive structure made of quantum information and entanglement. The third dimension may be a kind of holographic projection from a two-dimensional surface. Space-time, in this picture, is not the stage on which physics happens. It is itself a kind of physics, built out of more fundamental ingredients. The geometry of our world, in some sense, is a consequence of the way information is organized at deeper levels. To ask about the interior of a black hole is, in this picture, to ask about how information is encoded on its surface, and the apparent interior is just one of several equivalent ways of describing the same underlying reality. There is something almost dizzying about contemplating these ideas. The universe we live in, the universe of solid objects and three-dimensional spaces, may be far more flexible and contingent than we ever suspected. Space itself may be a kind of woven fabric, knit together out of quantum correlations between systems that exist at some deeper level we cannot directly access. Time itself may be similarly emergent. With the smooth flow of causality we experience arising from some more primitive structure, where there is no fundamental distinction between past and future. The work on black holes has not yet given us complete answers to these vast questions, but it has given us clues, and the clues are pointing in remarkable directions. When we look up at the night sky and see the supermassive black hole at the center of our galaxy, captured for the first time in direct imagery by the Event Horizon Telescope collaboration in 2022, or the supermassive black hole at the heart of the MADI 7 galaxy, first imaged in 2019, we are looking at something far stranger than mere cosmic vacuum cleaners. We are looking at memory devices, archives of cosmic history, devices that may know more about the universe's past than any other object in it. Sagittarius A, a star, the 4 million solar mass black hole at the heart of the Milky Way, carries within its boundary an information density that defies imagination. The supermassive black hole at the heart of the MADI 7 galaxy, with its mass of about 6.5 billion solar masses, is in this view a holographic library of unfathomable depth. Every photon of its accretion disk, every infalling particle, every gravitational ripple that has ever passed through its event horizon, all encoded, all stored, all preserved in patterns of quantum information, so dense and so intricate that the entire informational output of human civilization, from the cave paintings of Lascaux to the most recent scientific papers, would constitute only an infinitesimal fraction of what is recorded there. And it is not just the supermassive black holes. The merging stellar mass black holes detected by the LIGO and Virgo collaborations, those gravitational wave events that have been routine in physics since the first detection in 2015, are themselves carriers of immense informational content. Each detection of a binary black hole merger is, in some sense, a detection of two cosmic libraries combining their archives into a single, larger library, with the merger itself producing a brief flash of gravitational radiation that contains within it subtle correlations encoding the histories of both merging objects. Future gravitational wave observatories, including the space-based LISA mission scheduled to launch in the mid-2030s, may begin to detect even subtler features that test some of the theoretical predictions about how information is stored. The implications for cosmology are equally striking. If information cannot be destroyed, even in black holes, then the universe as a whole is constrained in ways we are only beginning to understand. Every event in the history of the universe leaves some record, some trace, some imprint that persists in the patterns of correlation between particles, in the structure of spacetime itself, in the entropy that accumulates as time passes. The arrow of time, the direction in which entropy increases, may itself be a consequence of how information is organized, of the way pasts have less entropy than futures in our particular corner of an enormously larger cosmological structure. These questions remain open, but they are now being attacked with tools that did not exist 20 years ago, tools forged in the long struggle to understand black holes. There is something almost reassuring about this picture. We live in a universe that, at least in this sense, refuses to forget. The histories of every object, every collision, every quiet moment in some cold corner of space are written down somewhere, preserved by the strange and beautiful interplay of gravity and quantum mechanics. We may never read those records. The encoding is dense, scrambled, holographically projected through dimensions we cannot directly access, requiring computational resources and theoretical understanding that may forever exceed our species' capacities. But the information is there. The memories are real. The universe is, in this very precise sense, a place where the past matters and is preserved, even if no one is around to read it. Of course, this is not the end of the story. Major questions remain. We do not yet have a complete theory of quantum gravity, and until we do, parts of this picture remain conjectural. The island formula has been derived in detail for certain idealized situations, primarily in two-dimensional models of gravity and in ADS/CFT setups. And the picture in the real, expanding universe, with its dark energy and its cosmological event horizon, is still being worked out. Whether ER equals EPR is literally true, in the strong sense that every entangled pair corresponds to a real wormhole, or just a useful heuristic, is still debated. The fuzzball program has produced beautiful results in special cases, but has not yet been fully extended to ordinary astrophysical black holes. The soft hair proposal continues to generate new work and new controversy, with refinements and counterarguments appearing regularly in the physics literature. There are also deep questions about how all of these pictures fit together. Are the holographic principle, ER equals EPR, soft hair, fuzzballs, and entanglement islands different aspects of the same underlying truth? Or are they competing pictures, only some of which will turn out to be correct? Most theorists now believe they are complementary perspectives on a single deep structure, but the precise way they fit together is still being worked out. There are tensions and apparent contradictions between different approaches that have not yet been fully resolved. The history of physics suggests that such tensions usually point to deeper unifications waiting to be discovered, and the next decade or two of theoretical work may produce a more complete and integrated picture. What is no longer in serious doubt, however, is the basic conclusion. Information is conserved. Black holes are not the perfect erasers Hawking once thought. The bedrock of quantum mechanics, the principle of unitarity, has survived the longest and most serious challenge ever mounted against it. And in surviving, it has dragged our understanding of gravity, of space, and of the nature of reality itself into strange new territory. If there is a lesson buried in all of this, beyond the technical victories and the mathematical surprises, it is perhaps this: the universe is more interconnected, more subtle, and more careful with its own history than we ever had reason to suspect. Things that look like they are destroyed are merely transformed. Things that look like they are lost are merely hidden. The cosmos is a great archive, and the dark stars at the centers of galaxies are among its most faithful librarians, holding the memory of everything that ever fell into their embrace, patiently, across timescales that dwarf the age of our universe. There is also a beautiful kind of intellectual humility in this story. The greatest minds in physics, Hawking, Bekenstein, Susskind, T. Hooft, Maldacena, Penrose, and so many others, spent decades disagreeing with each other, arguing, revising, sometimes admitting they were wrong, sometimes doubling down on positions that later turned out to be partially correct in unexpected ways. The picture that has emerged is no single person's victory. It is the slow, collective work of an international community of thinkers, each contributing their own piece to a vast puzzle that none of them could have solved alone. Hawking himself, who began the entire saga with his audacious claim about information loss, eventually conceded that he had been wrong. But his original work remains foundational, because the questions he asked were the right questions, even if his initial answers were not. Bekenstein's seemingly absurd suggestion about black hole entropy, dismissed by many of his elders, turned out to be one of the most important ideas in 20th century physics. Suskind's stubborn refusal to accept information loss drove him to develop ideas that have reshaped physics. The story of black hole information is, in this sense, also a story about how science actually works, about how progress emerges from genuine disagreement and patient argument. The next phase of the story will likely involve sharper tests of these ideas, both theoretical and possibly observational. Theorists are working to extend the island formula to more realistic scenarios, to better understand the role of replica wormholes, and to develop the implications of holography for cosmology. Observationally, gravitational wave astronomy continues to refine our knowledge of how real astrophysical black holes behave, with detections of mergers providing precise tests of general relativity and its quantum extensions. The Event Horizon Telescope continues to produce ever more detailed images of supermassive black holes. Future experiments may even detect subtle features predicted by some of the more exotic proposals, features in the gravitational wave ringdown of merging fuzzballs, for instance, or subtle deviations from the predictions of the no-hair theorem. We may also be approaching a moment when laboratory experiments begin to play a role. Analog black holes, created in fluids, optical fibers, and ultra-cold atomic gases, have already been used to study Hawking-like radiation in controlled settings. In 2022, an experimental group in Israel created an analog black hole out of a sound wave in a Bose-Einstein condensate and reported observing Hawking-like radiation. Though the analog setting limits the direct relevance to gravitational black holes, as these techniques mature, they may provide laboratory windows onto some of the phenomena that have been so difficult to test directly. Information theory, quantum gravity, and experimental physics may finally come together in ways that allow us to probe these deepest questions in a more direct fashion. There is also growing interest in connections between black hole physics and quantum computing. Some theorists, notably Patrick Hayden and John Preskill, have explored the picture of black holes as quantum computers that scramble information at the fastest possible rate, consistent with the laws of physics. In this view, what black holes do to information is essentially what a powerful quantum computer does, taking inputs and processing them into outputs through complicated unitary transformations that mix the input bits together so thoroughly that they cannot be easily distinguished from random noise. The scrambling time, the time it takes for a black hole to thoroughly mix the information of an infalling object into its existing state, has been the subject of much study. For a typical black hole, this scrambling time is proportional to the logarithm of the black hole's entropy, divided by its temperature, which works out to be very fast indeed, far faster than for any classical system. Black holes are, in this picture, the universe's fastest scramblers, the natural endpoint of any process that takes information and mixes it as thoroughly as the laws of physics allow. This connection to quantum computing has practical implications. Some of the techniques developed by quantum information theorists, originally for analyzing quantum error-correcting codes and the limits of quantum cryptography, have turned out to be directly useful for analyzing black hole information processing. Conversely, ideas from black hole physics have inspired new approaches in quantum information theory, including new ways of thinking about how quantum information can be hidden and protected. There is a growing sense that the deepest principles of gravity, quantum mechanics, and information theory are aspects of a single underlying structure that we are only beginning to discern. The story also has implications for how we think about the very early universe. In the first instance after the Big Bang, conditions of extreme density and energy may have produced primordial black holes, tiny ones that could have masses ranging from the very small to the very large. Hawking himself proposed in 1971 that such primordial black holes might exist, and they have remained a subject of interest ever since. Tiny, primordial black holes would have evaporated long ago, releasing all the information they contained back into the universe. The patterns of that release, if we could observe them, might give us direct insight into the kinds of mechanisms that preserve information during black hole evaporation. Some theorists have even speculated that the dark matter, the mysterious unseen substance that makes up most of the matter in the universe, might consist of primordial black holes, although current observations strongly constrain this possibility. For our solar system, the implications of all this are at once striking and humbling. The Sun itself, if compressed below its Schwarzschild radius, which is about 3 kilometers, would become a black hole. It is not going to do so, because the Sun is not massive enough to undergo gravitational collapse at the end of its life. It will eventually swell into a red giant, shed its outer layers, and leave behind a white dwarf the size of the Earth. But more massive stars, those greater than about 20 solar masses, will end their lives as black holes. And our galaxy contains an estimated 100 million such stellar mass black holes scattered through its volume. Most are invisible to direct observation, detectable only when they happen to be paired with a companion star that they can pull material from, producing X-ray emissions that astronomers can see. Cygnus X1, the famous source identified in the 1960s and definitively shown to contain a black hole by the 1970s, is the prototype of this kind of system. Each one of those 100 million black holes carries within its event horizon an enormous archive, the encoded record of whatever fell in across the billions of years since the black hole's formation. The supermassive black holes are even more striking. Almost every galaxy of any significant size contains one at its center. Our own Milky Way's supermassive black hole, Sagittarius A, is relatively modest, about 4 million times the mass of the Sun. The supermassive black hole in Mate 7, imaged by the Event Horizon Telescope, is more impressive, weighing in at about 6.5 billion solar masses. The most massive known black holes, found at the centers of huge elliptical galaxies, can weigh tens of billions of solar masses. Each one is, in the view that has emerged from this 50-year struggle, a cosmic archive of breathtaking scale. The patterns of information stored on the event horizon of Mate 7's central black hole could, in principle, contain the encoded histories of every star that has ever fallen into it, every cloud of gas that has been swallowed, every photon of starlight that has fallen across its boundary during the billions of years of the galaxy's existence. These are libraries that put any human archive to shame, written in a language we are only just beginning to understand. So the next time you look up at a clear night sky, and let your eye wander to a place where you know a black hole lies, whether it is the famous one in Cygnus X1, discovered in 1964 as the first widely accepted black hole candidate, or the supermassive ones at galactic centers that anchor entire galaxies in their gravitational embrace, or the merging pairs whose gravitational waves now reach us regularly across cosmic distances. Remember what you are really looking at. Not a hole, not an absence, not a place where things go to disappear. A vast, dark, profoundly silent vault of memory. A library written in a language no one yet knows how to read. A piece of the universe that, against all our intuitions and against many of our initial fears, never truly forgets. Consider what this means on a personal level. Every photon that has ever left your body, every infrared photon emitted by the warmth of your skin, every reflected photon that bounced off your face on its way to other surfaces, every radio wave from every device you have ever held has been carrying information about you out into the universe at the speed of light. Most of it has long since left our solar system. Much of it will eventually intersect with a black hole somewhere in the cosmos, whether the supermassive one at the heart of the Milky Way, or one of the countless stellar mass black holes scattered through the galaxy, or some other gravitational well in some other corner of the universe. When that information falls into a black hole, it is not destroyed. It is added to the cosmic archive. The memory of you, in some abstract sense, becomes part of the permanent record of the universe. This is not consolation. It is not metaphysics. It is just the physics that emerges from the deep mathematics of unitarity, holography, and quantum gravity. The universe stores everything. Black holes, those dark and once-terrifying objects, are not the destroyers we initially feared. They are the keepers. They are the cosmic libraries that hold within their boundaries every detail of every history that has ever fallen into their embrace. And perhaps the deepest lesson of all is that physics, in its long, patient struggle with the black hole information problem, has discovered something we did not expect to find. The universe, examined closely enough, turns out to care about memory. It builds memory into its deepest structure. It encodes histories with a fidelity that would put any human archive to shame. The cosmos remembers. It remembers stars that died 10 billion years ago. It remembers civilizations that may have arisen and fallen on planets we will never see. It remembers the particular arrangement of every atom in every page of every book that has ever been thrown into a fire. And it remembers everything that has ever fallen into a black hole, holding it patiently, written in a language of holographic entanglement and quantum geometry, waiting for someone, someday, perhaps, to learn how to read. There is also something here about how we think about loss in general. The universe, taken as a whole, does not lose things in the same way that we do. From a sufficiently elevated perspective, every event leaves traces, every interaction preserves information, and every history is written down somewhere. The forgetting that we experience in our everyday lives is a kind of practical forgetting. A forgetting that comes from our inability to access the records that are still, in principle, available. We cannot reconstruct the burned book from the smoke, not because the information is gone, but because we lack the precision to read what the smoke says. The same is true of our memories, our histories, our cultures. The information persists, scattered through the universe in patterns of correlation that we cannot easily decode, but it is not destroyed. It is just inaccessible. The cosmos is a much more careful keeper of records than we are. This careful keeping has consequences for how physicists now think about other extreme situations in the universe. The Big Bang itself, that singular event from which everything we know emerged about 14 billion years ago, is now understood as a place where the laws of physics break down in much the way they break down inside a black hole. The work on black hole information has provided tools for thinking about what happens at the Big Bang. Tools that suggest that the information about the pre-Big Bang state of the universe, if there was such a state, is not necessarily destroyed, but may be encoded somewhere, in patterns we have not yet learned to recognize. Some theorists have explored the possibility that our universe is itself, the interior of a kind of cosmic black hole, with our observable universe corresponding to the inside of an event horizon in some larger meta-universe. Whether or not this is literally true, the connection between black hole physics and cosmology has become one of the most active areas of theoretical physics. There are even philosophical implications. If the universe is, at its deepest level, a kind of vast memory device, an enormous web of correlations that preserves the histories of everything that has ever happened, then questions about meaning and significance take on new dimensions. The lives we live, the things we do, the people we love, the books we read, and the songs we sing, all of these leave permanent traces in the structure of reality. Whether anyone ever accesses those traces is a different question, but the traces are there. The cosmos, in this view, is not the indifferent vastness it is sometimes portrayed as. It is a place where everything matters in a very precise informational sense, where every event contributes to the ongoing structure of the whole, where nothing is ever truly forgotten by the universe as a whole. These are conclusions that physics, 50 years ago, would have considered absurd. The idea that black holes might be cosmic memory devices, that information is preserved through the most extreme gravitational situations in the universe, that the very geometry of space might be built out of patterns of entanglement and information, would have sounded like wild speculation in 1976, when Hawking published his information loss paper. Today, these ideas are mainstream theoretical physics, supported by decades of careful argument and recent breakthrough calculations. The journey from Hawking's original claim to today's picture has been one of the most remarkable in the history of science, and it is not yet over. The next decades will likely bring further refinements, sharper calculations, perhaps experimental tests that we cannot yet imagine. For now, though, we can say with confidence that the universe is far stranger and far more careful with its own history than anyone ever expected. Black holes are not the holes in space we once feared. They are dense concentrations of cosmic memory, holographic libraries written in languages we are slowly learning to read. And every time we look up at the night sky and contemplate the vast darkness of space, we should remember that some of those dark patches are not really dark at all. They are glowing, in a sense, with information. They are storing, with extraordinary fidelity, the histories of everything that has ever fallen into their embrace. They are the keepers of cosmic memory, and we are only just beginning to appreciate what that means. You have been watching, and we hope you have enjoyed this exploration of one of the strangest and most beautiful frontiers in modern physics. If this journey through the mystery of black hole information has fascinated you, if it has changed the way you think about the dark hearts of galaxies, please consider liking this video and subscribing to the channel. There is so much more to explore together. Leave us a comment and tell us what you think, whether you find Hawking's original picture, the holographic principle, ER equals EPR, the fuzzball proposal, or the island formula to be the most compelling part of the story. Tell us which mysteries of the cosmos you would like us to investigate next. Thank you for spending this time with us, and we will see you next time.